Hello everyone. Welcome to this lecture series of engineering mechanics, and in this video we'll be discussing about the dynamics part of rigid bodies, in which we will be learning how to apply the Newton's second law of motion to different rigid bodies. And we know that the Newton's second law of motion actually um, is dynamically oriented equation, in which we have the forces applying on the body, and it is compared to the especially the acceleration of the body, and mass times the acceleration of the body. So the concept involved is that the velocity is changing continuously, and that is how the body is actually in a dynamic situation. So how we will solve such problems in which the body is actually moving? So we'll use Newton's second law of motion to solve different types of set of problems. So we will start. Now, as I said that there are different forces acting on the body. Like for example, in this case, we have a wheelchair, and uh, this man is actually pushing the wheelchair in this direction. However, there are certain forces. One is the weight of the uh, wheelchair, which is actually pushing the wheelchair, and since the weight is in the downward direction, but the component of this downward direction is there in this slant direction, or in the backward direction, which is backward to the applied force. And further, we'll be having a friction also. So friction forces will also be there. So if a man has to push the wheelchair forward, he has to counter this weight, overall weight here, that includes his weight and the weight of the wheelchair. uh, and further, he also has to counter the friction. So these forces are important. Why they are important? These are important because um, it should be it should be said that the force applied by this man should be feasible. This should not be very large. Okay, so the forces should be feasible to apply. It should be easy to apply, and that is what the ramp designing means. That means if he wants to move the wheelchair forward, he has to apply as much lesser amount of force as required. So it is important to design such ramps in a good and the proper way, so that if we have a ramp at a very higher inclination, if this inclination is, let's say, 15 degrees, and we have designed the inclination at a very high angle, let's say 45 degrees, then this inclination component of the mg, this is mg component, and the inclination and mg will be here, which will be, if this is cos theta, this will be mg sin theta. So this component will be very large, because this sin theta will be increasing sin theta. So this needs to be designed in a proper way. If we will keep this properly horizontal, then this man would not be able to actually go in the upward direction, or somewhere above the stairs. So we have to move him, to move him on the upper terrace or somewhere. These inclinations, you might have seen these inclinations nowadays in most of the institutions and private sectors also. So the analysis of force becomes very important. Now we know what is Newton's second law of motion. That means the summation of all the forces acting on a body must be equal to mass times acceleration of the body. And we know that the acceleration should be, that means the force should be in the direction of acceleration, should be in the direction of the force. So this is a force vector, and this is the acceleration vector. We know about the Newton's second law of motion. So what is something important about it? If we make some adjustment Like if we write the expression in a derivative form, we can derive one another very important term which is known as momentum. Now we all know what is momentum. Momentum is mass times velocity of the particle. So we used to say this mv as a linear momentum of particle. You must have studied about momentum um, in your physics classes, 11 12 classes. So there it was a word only as a momentum only. However, here we're discussing about two types of momentum. One is a linear momentum, which is experienced by the body when the body is moving in certain curves. In certain curves, when the body is moving, there is a linear momentum experienced by the body. And if the body is actually moving in a in some clockwise or anti-clockwise circular fashion, then the body experiences angular momentum with respect to the central theta. And we will discuss about angular momentum in the later part of the videos, or in this video only at the end of this lecture. So the conservation of linear momentum here, it's an important concept because it helps us to solve the problems of dynamics in a way that we have already known. That means the statics way of solving the problem. What was it? That sum of all the particles acting on the body is equal to 0. So we were able to solve such problems very easily. So that's what we'll do here also. We'll sum up all the forces or any other vectors available here, bring it to this side and sum it to 0. And we will try to solve the equations, something very similar to how the um, how we used to solve the statics part. So we'll see for this, and we know that the force component here will be along the x, y, and z directions. So the force and acceleration component. Remember that mass does not have a component. Remember that mass is a constant quantity. It's a scalar quantity. It does not have a components. Weight will be having a component. Okay, weight will be having a component along these directions. So weight may be having a component, but not mass. Okay, so we have ax, ay, and az are the special components of acceleration along the x, y, and z directions. In a similar way, so these I, j, k can be compared, and some of the forces along x can be compared to the masses times acceleration in the only in the x direction. In a similar way, this can be achieved in the y and z directions also. Now, as I said, we will like to solve the dynamic problem in a static way. So, as a dynamic problem, you know that the concurrent forces, there will be many concurrent forces. So, what about putting or transferring the ma to in this side of the equation and writing the equation in this form? And instead, since this is also a vector, ma times is a vector ma, so we'll put one vector for the ma also. This also becomes one force. So F1, F2 and minus Ma will become one another vector, and we call this vector as an inertial vector. We call this vector as an inertial vector. This is inertial vector because it contains inertia. Inertia, why? Inertia is something, a moving mass is called as an inertia. So mass is moving with the acceleration is called as an inertia actually. And in this case also, if like for example particle moving on a curvature, so we'll be having a tangential component and normal component. We have learned this in the previous lecture. So as many as forces you will take, you'll be having a tangential component of ma, and we'll be having a normal component of ma. Okay, so both these components will be having in a similar way. So apart from the forces, now in the dynamics part we'll be having another component known as an inertial vector or inertial component of the in x and y directions, or in t or n directions, or in r theta directions. Okay, so this is the additional component. Okay, So now important thing here, what is the advantage of doing this? One of the advantages is that I can use it in a static way. Okay, so one advantage becomes that the resultant of f1, f2 and f3 will be a closed polygon, like we used to make a closed polygon in our statics while we were solving the problems. So when we were making the closed polygon means that sum of, if the polygon becomes closed by summing up all the forces, okay, then that means this all is in equilibrium. So we can achieve equilibrium by doing this. So apart from this, we can use the statics way. We have also achieved an equilibrium part also. Okay, so now we know that these are all inertial components. So we'll try to see what is a free body diagram and what is a kinetic diagram. Now these two will be important. We'll try to compare a kinetic diagram and free body diagram. Like in this example, if you see this, a block is there and we are trying to pull the block out of the slant. So we have first of all isolate the body. So what is the body in interest? This is my body in interest, body B. So I'll isolate it. The next step will be like this. The next step will be draw your axis. We've drawn the axis. Then we apply the forces. Whatever the forces are there, apply it. These are the two existent forces. Remember that these are external forces, not the applied, and these are external forces and not the reaction forces, okay, or support forces. So these are the applied forces. We have checked it out, the applied forces. Then the support forces. So what are the support forces? One is the normal experienced by this block, okay, and another one is the friction force. And then if there is some dimensions of the block, use that in this way. So now once this FBD has been made, we will put the inertial terms and we'll make a kinetic diagram. So this is how a kinetic diagram is made. Now this is a free body diagram. We have made it in a proper way. Now we'll make a kinetic diagram. So this is the block we have taken, and the important thing is the movement, and movement is what is required in a kinetic diagram. So the movement will be MAX, one component along the x direction, another component along the y direction. This is called as a kinetic diagram of this free body diagram, and this will be equal. Why? Because sum of all the forces acting on a body is equal to mass times acceleration. This is what we used to do. We make a free body diagram and we'll equate it to the kinetic diagram. So as I said, okay, so we would draw the FBD for the block A, block B. This is a new situation to you. So you should draw a, first of all, isolate the body. Second, so we have isolated the body, axis, put the axis, applied forces. This is the only applied force, mg, weight of the block. There is no other applied forces, remember. As you can see, no external forces are there. These are all tensions. Okay, these are all tensions. So further, replace support with the forces. So we have support, replace the support with the forces. Friction forces there, support forces there, tensions are there, all these things are there. Dimensions drawn, kinetic diagram. And this is what the kinetic diagram looks like. Now, when I used to write the component MAY equals to 0, that means there is no movement of this body along the y direction. There is only the movement along the x direction. So I have to write this because I have written this MAX equal to 0, though I would not need to make this arrow and all these things, do not need to write. Only this component will be active because the slide can move in the x direction only. So this is how the kinetic diagram and the FBDs are made. Another problem is there, and we need to find the FBD and KD. Okay, So now the only thing or the only body that are in picture is body B. So we've isolated the body axis. We will work on r theta coordinates, because as you can see, this lever can move in these directions. Okay, this can move here and B can move in these two directions, up and down along this lever. So r theta will be the most appropriate coordinate system, because if you use xy, how will you trace the theta orientation? You will not be able to trace the theta orientation. Okay. Any applied forces? So mg will be the only applied force. Support reactions. One is the friction force you will experience while moving upwards, and another one is the normal force. Any dimensions we have placed. Now what will be the corresponding diagram? So MAR, one component here and another theta component. Okay. Now I hope that now you have understood how to make the FBDs and kinetic diagrams. So let's solve some problems now. So as you can see, this is one problem in which there is a block which rests on a horizontal plane. Inclined P is applied on this block, and the block moves with the acceleration of 10 feet per second square. The friction of the moving block is given as 0.25 kinetic friction. Find the magnitude of the force. So just simply put up all the forces along the x direction to an A. Acceleration will also be only along A. Okay. So we'll find out the acceleration A. Okay. So which are the component? First is P cos theta, horizontal component, and minus 2.5 N, which is the friction force. So these are the two. One is this component. Okay. Another is this component. Both are in the opposite directions. This equals to MA. M is this. A is 10 feet per second square given. So these are the two unknowns. Another is for the y. There is no component of acceleration in the y direction, so that is 0. So n minus p component mg, p sine theta, and the weight of the block also, that should also be subtracted because it's against the y. This is all equal to 0. So two equations, two unknowns, we can solve it easily, and we can find n and p. Okay, this looks very simple, and it is a simple problem, but the important thing is the application of this inertial component in the equation. This is something new for us and important here. Since there was no acceleration component in the y direction, we have not taken it. Since there were acceleration component in the x direction, we have taken it. If this would have been a static problem, we would have taken fx equal to 0. And the problem would have been solved something very similar to the way we have solved the statics problem. So this is something very similar what we have done till now. Another problem is there. Two blocks, and they will move, start from rest, and they are being pulled by using a pulley. Determine the acceleration of each block and tension in the cord. So the basic thing is to draw the FBD and kinetic diagrams. So we have drawn first of all draw the FBD only along the x direction. We have seen that this is the FBD, weight of the block, normal, and tension. This is equal to mass time acceleration. So there will be one acceleration of this block, another acceleration of this block. Okay. So one acceleration in the x direction, another acceleration in this direction. Okay. So this will be in this direction. So summation of same thing we have to do. Take the forces, tension equals to mass times acceleration, and this is also equal to mbg. That is, remember that acceleration in the b direction is the gravitational acceleration. So this is the set of g multiplied by g minus t2, tension here, okay, being pulled, mb ab. Okay, so this is solved and T1 and T2 is obtained. Now AA and AB is remaining, so we will add up one more equation. Uh, Very important to notice here that the other part that we have involved, the C part. See, the A will move and the B will move. But remember that the B and C will move together. B and C will move together. So A will move and B and C will move together. So you do not have to solve the equation for B and for C. It is not required to solve the equation for C. But we are solving here the equation for C. Why? Because when we have solved the equation for X and for the Y, we are still having two unknowns. So the system becomes indeterminate because the number of variables are more than the number of equations. So we know that there is a relation between A and B. So one equation is less because there is a relation yb equals to half xa. There is a relation between them. At this length is half of this length. So since there is a relation between the expressions, so one equation is reduced. So we need actually one more equation. At least since three variables become four becomes three, so we need three equations. So we have additionally to solve this, to find one more variable, we have additionally taken one more equation. And due to that, we were able to solve this another situation by using these two equations. So we were able to solve these four variables that were required. So you have to put your thoughts on this, and this is an important problem, that why there is a requirement of another point to be seen. And remember that we cannot use the point D because D point is fixed. There is no movement of this D point. Okay? So there will be no forces. There is no mass here. So the acceleration part and something will not be there. There is no movement of D. So it is important that we will only select the point C. Okay. And further, there is one more thing, that the C point is also having a direct relationship with the body A. So there is two tensions here and there is one tension here. So this is actually also comparing. However, here there is nothing. This is actually fixed and this is related to this. If you relate these two, you will not be able to actually. So it's important that we should take C as a point in the additional equation. Again, this is one more problem. So we are doing actually a lot of problems in these lectures. This is one block of 12 lb which is moving on a wedge. So this block is actually moving on this wedge. We need to find the acceleration of this block and this block. Remember, when this will move on this block, when this block B will move, this may also at the end will push A. So we would need to find the acceleration of this and the acceleration of this. So these two we need to find the acceleration. So first of all, draw the FBD. Okay, and draw the kinetic diagram. So this is the FBD and the kinetic diagram. Simple FBD, normal reactions, weight, and remember there are two normals because there will be one normal from this side experienced by this on the top and one his own normal compared to the acceleration. Only acceleration in the horizontal direction. So we have solved this, obtained this equation. Another case for the block only. Block will experience only one normal because on the top of the block there is no weight anything. One is WV, his own weight. So we'll be having one component of this along this x direction and one is along the horizontal direction, which is at the 30 degrees. So just put this put along the x, we will put cos 30 degree here and we'll try to solve this. And it is important to see this figure, that the acceleration here, that the acceleration of the B is a relative acceleration because both are dependent on each other. So one acceleration of A actually is relative to B. So this is a relative thing. We have discussed this as a position vector in our previous articles, that what is the point A? What is the movement of A? Movement of A plus the relation between the two. What is the relative vector? So the relative vector will be moving in this direction. That means B to A, because B is on A. This block B is moving on A. So when it is moving, it will move relatively. One will move relative to another block. So using this, we have used the acceleration component on the B here. Okay, and we have used the relative vector. So we'll obtain the relation between the two accelerations, and the relative vector will be this along the B. So by using cos theta sin theta components, you can easily obtain this. Okay, try to solve these equations and you will be able to obtain the acceleration of A and the acceleration of B. Both of them you will be able to obtain by using these equations. These are very simple and straightforward problems. Only basic mathematical knowledge is required of the components, and that you have already gone through in your previous lectures. We have already gone through how to sum up the forces, what are these components. They do not need to be repeated again and again. Okay, and then the relative vector, acceleration of the relative vector BA. This is another problem in which, and if you see this problem, I can remember this. We have already solved this problem in the statics part, and we have put the constraint. Yes, we have solved this. So this was the XA and this was the XB, and we have put in an equation with the constant XA plus 3YB. We have solved this earlier. This is the distance XA and this is 3YB. Why this is 3YB? Because this is 1YB, 2YB, 3YB plus constant. These are the constant length not needed to be required, equal to the total length of the string. Total length of the string. Now we can differentiate this twice to obtain the acceleration. So this is, we have differentiated and obtained the acceleration component. Already we have done this, but we have not differentiated it twice to obtain the acceleration component. Okay, this we have not done. Further, FBD and KD diagrams, and so this is the FBD, simple FBD, and a KD diagram for you. And this is the for the B part. A part, this is the A part, and for the B part. These are self-explanatory, and we'll write the equation of motion for the A and B in both these terms. Equation of motion for B, equation of motion for A, sum of all the forces along the Y, sum of all the forces along the X. So the acceleration will include that. Okay, and solve these equations. Just solve them simply as you know how to solve them and obtain the acceleration. These are very simple, straightforward problems. Just you have to keep the concept with you all the time, what you are doing. If there is a movement, just try to put the acceleration component. If there is no movement, remove the acceleration component. And the component of acceleration should be along the axis chosen to define your problem. Now this is a concept quiz. I think you should do it by yourself, but let me explain this to you. These are the weights and these are being balanced by the another weight. Now the three systems are released from the rest. Rank the acceleration from highest to lowest. Okay, acceleration you have to rank. So which will experience the highest acceleration? Now this is something very, you might have seen this, that the acceleration component is very much related to the weight or the momentum of the particle. You might have seen this during a weight balance. So if you can see, this is 200 lb and this is 100 lb. 200 lb and only force 100 lb. This is 100 lb plus or multiplied by g also. There is a downward force of g which is acted. So there are two forces which are being multiplied together, mg. Sorry, this is force. So this is one force and this is the gravitational pull is also there. However, here only there is 100 lb force. And what is here? 21 lb weight. Now, what is acceleration? Let's define the acceleration. We all know the definition. Is the movement of this. How quickly it will move. How quickly it will change its velocity and increase its velocity. This will depend upon how much less weight here it is. The movement will be very high. That is acceleration. So, the less weight will be here. This will be helpful to increase the acceleration here. So, highest acceleration will be where there is a lesser weight, and where it is lesser weight, if you compare them, these are comparable, so acceleration will be least here. So third will be having least acceleration because the weights are comparable. Here the weights are half almost, but here g is also preventing this to accelerate. Here there is no g, only 100 lb force is there because g is already included in this. Only 100 lb force is there. So definitely this will accelerate the fastest, then this, and then this. I hope the reasons are very much clear to you. Oh no, no, okay, it's right. No? Two, one, okay, take it. So this is how we should solve or conceptualize these problems. Now the same F equals to ma will be having a normal and tangential components also, and we will see some of these problems in the other coordinate systems also. So Newton's second law of motion, second law of motion in the tangential and normal coordinates. We have already discussed about tangential normal coordinate. This is the tangential coordinate, this is the normal component. So when forces will have a component, why not accelerations? Acceleration will also have a tangential and normal component. Remember this, that the normal component will be having this v square upon rho as the velocity times the radius. And we will use these equations only to solve our problems in this coordinate system. Like in this case, there is a bob of 2-meter pendulum which is rotating or oscillating. The tension in the cords is 2.5 times the weight of the bob. Find the velocity and acceleration of the. So we have first of all defined the FBD, the tension, the weight, and this is the KD. Kinetic diagram will also have a component in the n and t directions. Sum up AT and find it out AT. Very simple problems. And the other one AN, sum it up and find it out the AN. We have to solve for the velocity. So AN will be having a velocity component, rho square upon v square upon rho. So we will able to find the velocity. This is another problem of a car which is which is having a speed of which is having some particular speed, and it is moving on a radius of curvature which is 400 feet. However, it is inclined blanked at an angle of 18 degree. Okay, the speed of the highway is also blanked to an 18 degrees. So what will be the speed of the car if there should not be any lateral friction between its wheel? So the important thing is here that this is how the car is moving. We have to find the speed of the car. The speed of the car, if there is no lateral friction, that means do not include friction for now. We have to find the speed of the car. Now, which coordinate system to be followed? Remember that the weight of the car is moving in this direction during the movement. During the movement of the car, there will be a weight of the car in this component, will be in this direction, trying to move away from the road. And there is no radial component because you do not know that the curve of the highway, what is the directly curvature of the highway and everything, you do not know. So you do not know the tangential component or something. So we have taken just a normal component, n, because this is the normal component, and we have taken any other axis, y axis. It's important to understand why we have taken the normal component here, because this weight of the car will try to push out of from the highway, trying to push this car out from the highway. So we have taken the normal component. We could have taken x also, but we have not taken x. We have taken normal component because we have to find the velocity, and the acceleration of the normal component will have a velocity feature, v square upon rho. En has a velocity feature, v square upon rho. X does not have a velocity feature. We have not taken that. And why we have not taken r? Because this is not r. This is vertical position. R will be along this curvature will be r. So then if we would have taken r. However, this is not r. Okay. And remember that this is reaction force, not a curvature. There's a reaction force coming up here. So you have to find the velocity. Let's see how this problem is solved. So the dimensions, everything we have written, this will be the MAN. Remember, this will be the momentum of the car. That how much momentum you will see in this normal direction. So this is the FBD diagram, this is the kinetic diagram, and we will try to solve this. Sum of all the forces along the y, only W we have, and r cos theta component along this. So we have one relationship. In the another case, we have normal component. So normal one, r sin theta, m upon an, m times an, and we'll have a relationship with the velocity. So we'll solve for this velocity of the speed. We'll solve for the vehicle speed, and we'll be able to solve it. So remember that why we have taken this n, because we need to take the advantage of the normal expression of the normal acceleration. We have to take the advantage of this, and the r will be along this only. So that's why n and t, tangential velocity, will be tangent to this now. So the tangential velocity will be facing something tangent. So this will not be tangent, this will be y, any other vertical direction. So normal direction and any other vertical direction. So in some specific problems, if we know the concept, we could also involve the two coordinate system together. Like in this problem, we have added, or we have combined the two coordinate system together. Remember that the x is also there. Where is x? This is in this direction, the x is, and y is also there. X is in this direction because this is a frontal problem, so I could not make it properly. This is y, so this will be x, radius will be this. So what is n? N is this. Okay, let's assume that car is moving along this direction. So tangential velocity is this. This is x and y. So x becomes almost same to n. If you have taken n instead of x, and tangential t is not required because it's not even asked and it has no role here. So only n and y has a role. So we have both the coordinates here included, but we have taken the best of the two, and that is how we have solved the problem. This is one other concept where we have driving the car and you have to draw the acceleration on these paths. I request you to do it by yourself. This is our basic problems, and so this is how the acceleration. Just see these A, B, C, D, what they are saying, acceleration, about acceleration, and try to draw them by yourself. Okay. Now another kind of coordinate system, as we know, the curvilinear feature, radial, and the transverse component. We will not discuss this too much because you already know about radial or the polar coordinate systems. So we know that the polar coordinate systems are like this, Fr equals to ma, and what is acceleration Ar? In the previous lecture we have discussed r double dot minus r theta dot squared. You have to remember that, learn that. Keep this in your mind. What is AR? AR is this. and a theta is this, because this will be used in the problems. While solving the problems, they will be used. So we'll solve a problem on this. This is one kind of a collar which is being pulled and pushed by the string, arm attached, and this is a drum which is, while rolling it, brings this collar closer to it, and while releasing it, brings this collar opposite to it. So simply r theta coordinate system you can use, a polar coordinate system, and you try to make the FBD and KD like this and try to solve it. This is already given in this. I request you to do it for yourself. Okay, write the equations of motion as you have written. Similarly, I've been told many times, just since you are using r theta, replace them r theta times r theta and put these equations. Now you require r double dot and theta double dot. Just obtain them. How you can obtain the expression for r and theta? This is already given. Theta dot equals to 0.75 t. Differentiating it twice, we will obtain theta double dot. R dot, that is velocity, is given 5 meter per second. Obtain r double dot by integrating. And then just substitute it in these equations already given to you and obtain the required expression of time, which is 2 seconds. So just do it for yourself. This is very easy, self-explanatory problems. Okay. A conceptual quiz. We'll discuss this quiz. A girl starts walking towards the outside of this spinning platform. This is a very famous jhula of children. You might have seen these in park, where people used to actually run in this curvature form, and they used to then jump on this prop. So they used to run in this curvature, though, or run or walk. This is what the girl is doing, walking on around this spinning platform as being seen. She is walking at a constant rate. Is walking at a constant rate. That means there is no acceleration. Rate of movement is constant with respect to the platform, and the platform rotates at a constant rate also. That means there is no angular velocity. So that means no angular velocity, no acceleration, but the velocity is there. So in which direction the forces act? So very simple. One is the tangential direction or even direction, along the even direction, and the another force will be, what will be another force? One force, he is trying to push this platform, trying to give his forces to a platform. So at each and every point he'll be having a tangential force. And one, due to the inertia of this platform will try to give the force back to this girl standing here. So this is E2 is, this is against this, so this will be minus E2. The direction is here, this direction is here, this will be minus 2. So we'll be having two forces, one is E1 and one is minus E2. So I think these two will be there. Forces along this and along this. One is along the tangential because of your movement, and another is this platform will give a equal and opposite force to you. This is very much similar to Newton's third law of motion, which actually, to every action there is equal and opposite reaction. Something very similar actually. That is it is. Okay. Now, before we'll close this session, we'll give a very brief introduction about angular momentum of a particle. This angular momentum is experienced by satellites which moves around the Earth orbit. So they move with an angular momentum. Okay. Remember, there is something called as angular velocity. Okay. And in a similar, we'll say angular momentum. So angular momentum is mass times acceleration in an angular fashion. So this is the Earth as you can see, this is Earth, and satellite used to move all around the Earth. So angular momentum concept becomes important. And what exactly angular momentum is? So angular momentum is your radius times mv, the moment of momentum. So this is the moment of momentum. So momentum is mv, and we have taken the moment of this momentum times r. So this becomes angular momentum. Remember, we have one a linear momentum which used to trace the particle, the tangential part, mv will be there. Okay, in this case, like for example, this is the particle, this was the tangential wave mv. So mv is the linear momentum, and if you take the moment of this momentum, that means r times mv, which is on one plane, there will be a vector which is perpendicular to this plane, and this is called as an angular momentum of a particle, represented by ho. Okay, and this ho will be having a magnitude. We know that r mv sine theta will be having its magnitude. It can be solved using simple determinant equation ijk. Just write it in this form like we have done earlier while doing the statics. And similarly, the angular momentum mv, as the linear momentum has the components mvr and mv theta, angular momentum will also be having a component mvr mv theta. Okay, and it can be added also, like we have added the vectors. So in this way it can be done. And so there will be many angular momentum, summation of all the angular momentum at a particular point. Okay, so I hope this video would be informative to you. If you have any problems, any questions, please write down in the comment section, and we will try to help you out. Thank you very much.